The flow of water is the essence of hydrogeology, and there are two important related concepts that we need to make sure that we're straight on before we start. Okay, so these are the two terms, flow rate and flux. So flow rate, what I mean when I use this term is the volumetric flow rate. So I'll use the letter Q, capital Q, to mean a volumetric flow rate, and that'll be a volume of flow per time. Those are the units. So gallons per minute, GPM, liters per minute, cubic meters per second. In streams, we often use cubic feet per second. All of those things are volumetric flow rates. Flux is the volumetric flow rate per unit area. So if we've got some volume moving along, it goes through a unit area. And the rate at which it's going through a unit area is the flux. So a volumetric flux is a volume that goes through an area per time. All right, so it turns out there are lots of volumetric fluxes in hydrogeology. So let's just make sure we've got the concept down. We've got a volume of water here, and that's going to be flowing, and it'll move through that unit area. I guess my little scribble here didn't make it along for the ride. But anyway, you get the idea. It goes through that unit area. And so this is the volume. That's the volume. This is the area that it's going through. And it happens in a unit of time. An example of flux is the way that we measure rainfall. So we have some rain, it falls into a rain gauge like this, and we measure the volume. And so this is graduated, and the graduations allow us to measure the volume of water that's collected. So we take that volume and we divide it by this cross-sectional area, the cross-sectional area of the collector, and that's how we express the amount of rain. It's this volume divided by that area. And so if we have an inch of rain, that's a volume divided by an area. And if we do an inch of rain in an hour, that's a cubic inch per square inch in 1 hour. So rainfall rate is a flux. When we're talking about water, we'll be using a volumetric flux, but there are a variety of other fluxes that are also useful. When we're interested in transport of contaminants or other types of compounds, then we're interested in a mass flux. And here's the rule. The flux of blank will be equal to blank per unit area per unit time. So a mass flux is a mass per area per time. So if we were interested in a mass flux of contaminants, it would be the mass of contaminants here that is moving through this area in a unit of time. We also have an energy flux. A common way that this crops up is the energy flux from the sun. And you might have guessed that's energy that goes through a unit area in a unit of time. Okay? So all of these different types of fluxes are just different flavors of this general definition of flux. The flux of something is the movement of that something through a unit area in a unit of time. There's that nice graphic. Can't get enough of that graphic. Here are two related terms, flux and average velocity. If we have a volumetric flux, volume per area per time, well, we can write that in terms of basic units. A volume would be a length cubed, an area is a length squared per time. And so if we reduce this down, the lengths cancel, and we get, as the basic units of volumetric flux, a length per time. Well, that has units of velocity, or it's the same units as velocity, feet per second, for example. Flux has the same units as average velocity, but it's really quite different. And let's take a look. Here's an example where we have this pipe. In this case here, the pipe is completely filled with water. So the flux is the volumetric rate divided by the area of the pipe, the total area. Okay? The average velocity will be the total volumetric flow rate divided by the area through which the flow is going. That's how we define the average velocity. We see that the flux through this pipe is the same as the average velocity because the pipe is full, so the area through which the flow is going is the same as the area of the pipe. But that's not always the case. In this case, we only have flow going through that part of the pipe. So in that case, the flux, we calculate it with this cross-sectional area. The total area of our pipe hasn't changed. But in this case, the velocity, but in this case, the area through which the flow is going is smaller than the total area. So the average velocity will be greater than the flux. So in some cases, it's equal, but in other cases, the average velocity is faster than the flux. We can take this principle and apply it to the flow through porous medium. So here's our pipe, and it's filled with sand. And what we see here is that the flow is going through the pores in between the sand. And so if we think of the pore space, kind of the cross-sectional area that's presented by the pores, that would be the area of the flow, the area through which flow is possible. And that will be less than the total area of the pipe, because in this case, the sand fills some of the pipe. But what we see here is that the flux, in this case, will be less than the velocity through this sand-filled pipe, for the very same reason that the flux was less than the average velocity on the previous slide, because the flow is only going through a fraction of the total area. It's not going through the entire area.